Hi guys, in today's lesson, we're going to be deriving the various formulas under the circular motion. In our previous lesson, we did a very breathtaking job on and the introduction, to circular motion. So today we're going to be deriving a couple of basic formulas that we're going to be using to solve questions on circular motion. So today we are going to start with the very basic ones that has been said. So today we're just discussing what we call the linear. Don't forget the linear is set as tangential. The linear or tangential and angular, or sometimes we call angular centripetal, linear tangential and angular displacement. This is what we're going to derive driving formula for this very two quantities today. So we're going to look at how we can derive the formula for linear distance of displacement and then angular displacement. So let's see how we go about that. First of all, we're going to be using um, a uniform circular motion. Let's do that. We're going to be using this, and also not only uniform, also horizontal circular motion. That's what we're using. So you have a body being whirled like this at a given angle. Now, at this very point in time, you have a speed at point A, velocity of A. At point B, you have a speed, velocity of B. Now, the fact is this. Now, there's a fact. We are discussing two things. Don't forget the first is angular displacement, and the second is linear or tangential displacement. That's what we are discussing. We are discussing these two major quantities. So now what's going to be the formula for angular displacement? Now, angular displacement, since you're talking about circular motion, angular displacement doesn't have any major formula. As you can see, the angular displacement you're talking about here is simply theta here. But we are talking about a very small angle, a very tiny angle. We're not talking about a big angle. And that's why this very angle here cannot be in degrees. This angle here will be in radians. Now watch, theta is in rad as radians. Radians is simply an angle in a circle. The angle we have in a circle. Now there's a circle here. There's the center of the circle. Now there's a radius. These are the radiuses or the radii. So the angle we have in a circle is what we call radians. So we also call it rad, R-A-D, in short. So this theta is in radians. Theta is in radians because we have a very small, because we have a very small angle. Now, theta is in radians because we have a very, very small angle. Now, what is going to be the angular displacement? The angular displacement, the angular displacement, the angular or centripetal displacement, the angular displacement, I can call it distance displacement, whichever, is the same thing as theta. We're going to take theta as the angular displacement. Now, why is it so? The reason is so because it's simply this. You're talking about angle. We're talking about angle. So, for the we are talking about angular. What we're talking about here is angular. And the movement takes place from here to here. The movement is very, very minute, very small. So, we assume that this theta is the angular displacement. This is the angular displacement. So, angular displacement is theta. So, if angular displacement is theta, now what's going to be the linear displacement? The linear distance. The linear displacement, either linear or tangential. Don't forget, everything we do here under circular motion, as I said, we are mainly divided into two parts, two parts. We have the linear or tangential. So as the body moves in a circular path like this, at a point in time, as body at this very junction, as it's going like as moves at this junction, the body faces this direction. It continues on to this very place. At this very junction also, it faces this direction. It looks like it wants to break out. Now, due to the help of what we call centripetal force, the centripetal force that keeps bending it towards the center of this whole circular path. In our centripetal force, probably this object or this very bulb would have broken out like this. So this thing is about to break out, but centripetal force keeps it going. At this very junction also, it faces direction. Centripetal force keeps it going, just keeps it going like this. Don't forget, we also have other stuff we're going to be discussing, but we're mainly focused on linear and angular displacement. So angular displacement is theta. That's angular displacement. So what is linear displacement? Let's see what linear displacement is. Now, the linear displacement is simply the gap from here to this place. The gap from point A to point B. That is the linear displacement, just from here to here. So now what does this thing look like? This looks very much like an arc for those that are basic understanding of mathematics. If you don't understand basic mathematics, there's no way you'll be able to understand this. So the linear displacement or the tangential displacement is simply the distance from this very spot to this very spot here. Unlike the angular displacement or the angular distance, which is theta, because of the fact you're talking about a very small angle. So the linear displacement is equals to length of an arc. The linear displacement is got the length of an arc. So if the linear displacement, which you're going to represent using S, is length of an arc, so the question is, what's the formula for length of an arc? Length of an arc is simply theta over 360. That's a portion, a small portion. This theta is in degrees. Theta in degrees. Let me just write that. Theta in degrees over 360 times the circumference of the circle, because this is a part of the circumference of the circle, not the whole circumference. So theta over 360, theta in degrees over 360 degrees times 2 pi radius, 2 pi r. So this is for length of an arc. There's a formula for length of an arc, which is the same thing as the linear distance. So don't forget this theta here, which is angular distance, is in rad. This theta in rad. Why? Because you're talking about a very small angle. This theta is in radians. So if you're talking about theta, the theta here should be in degrees, not radians. And the theta we have here is in radians. So we have to look for a way to convert this theta in radians to theta in degrees. So once we do that, we fix it into this, and then we can easily get our formula for linear displacement. So let's look for a way. What's the relationship between radians and degrees? It's very simple. Mathematics will help us out here. What's the formula for circumference? Circumference is 2 pi radians, or 2 pi radius. Radians and radius are their family. Radian is simply the angle, gotten from the two radiuses and the length of an arc. So circumference is 2 pi r. So the total angle in the circle, in the circumference of the circle, is 360 degrees. So the circumference is 2 pi r, which is equal to 360 degrees. 360 degrees is the total circumference, like the total angle, total degree in the circle. So this 2 pi r is 2 pi times 1 rad, let me use that word, 1 radian, equal to 360 degrees. So let's try to get a relationship between them. So 1 rad now, we're going to divide both sides by 2 pi. 2 pi. So 1 rad, which is 1 radian, is 360 degrees over 2 pi. 2 here 1, 2 here 180. So 1 rad is 180 over pi, 180 over pi degrees. You can use a calculator to do that. So 1 radian is 180 over pi degrees. Now, if 1 radian is 180 over pi degrees, then theta radian, because this theta, the angle we want to use is in radians. We want it to be in degrees. So theta rad or theta radians will be what? How many degrees? X degrees. So proportionality knowledge. So 1 times x is x, theta times 180 over pi. So the theta rad is equals to 180 theta over pi. That's what we have for that. So 180 theta over pi. Don't forget, circumference is 2 pi r, which is 360 degrees. It's the same thing as 1 revolution. Let's use that word. Do not forget that. It's the same thing as 1 revolution. So we can just probably link up everything. So if 2 pi, if 1 rad is equal to 360 over 2 pi, it's the same thing as equal to 1 revolution. We using this, and so we're going to come back to that. So what do we have? This 180 theta over pi. That's what this is. So we're going to take this now and put it right into this place. So let's finish up our derivation. Let's finish up our derivation of this formula. So let's see what we've got. So the distance, which is length of an arc, is equals to, what's the angle in degrees? The angle in degrees now is 180 theta over pi degrees. 180 theta over pi, then divided by 360 degrees, times 1 over 360 degrees, then times 2 pi r. So what do we have? This 180 here 1, 180 here 2, 2 here 1, 2 here 1, pi here 1, pi is gone. So what do we have? S is r theta. So this formula for linear displacement or tangential displacement. So this is formula. For angular distance or displacement, angular displacement is theta and rad, while linear displacement the is what we have is the angle which is in degrees. The angle sometimes could be in radians, it depends, times the radius of the circle. So these are the formulas for both linear and angular displacements. So we're going to draw the curtain on today's lesson at this very portion, at this very point I mean. If you found this lesson resources, please subscribe to this very channel at Edu Mosaic. Also follow me on Facebook at Revelation Hub. Share this lesson also with others. See you in the next lesson, and please watch out for the next lesson on linear and angular velocity. Thanks.